This robot can finally pick up objects, but 1 month ago, it couldn't even lift its own arm. If you've ever tried building a low-budget, 3D printed robot arm, you know the challenge. Getting cheap servos to move smoothly without awkward jittering or completely collapsing is hard.
Yes, I've been there.
In my last video, I built the first prototype of PicoPal. It moved, well, except for the shoulder, which completely fell under the weight. Today, I'm sharing my journey upgrading to version 2. I'll walk you through my design choices, the literal days of 3D printing struggles, and the 8 iterations it took to finally get a functional arm, so you don't have to make the same mistakes.
Let's build this together.
The biggest problem with V1 was obvious. The shoulder couldn't lift the arm. Originally, I used SG92R's micro-servo. It's cheap and lightweight. As I saw existing robot arms using it, I went directly into the design, thinking it's going to work.
Now I know skipping steps does not really save time.
So finally, I did a proper torque calculation with the worst case scenario, meaning the arm fully extended horizontally. Every part after the shoulder, like the 3D printed links, the other servos, the object in the gripper contributes to the shoulder joint torque. I crunched the numbers, added up 2.5 times safety factor to cover those mechanical losses, and the result was eye-opening. The shoulder was severely undersized, and the elbow was right at its limit. Suddenly, the failure made completely sense. The conclusion was clear. I needed more torque.
Now came the difficult part. How to fix it? I have 2 paths forward.
Path 1 was to keep the tiny servo and design a mechanical gear or belt reduction system. This is an elegant approach because it multiplies torque while keeping the arm incredibly compact, but it adds more 3D printed parts and more points of failure. Path 2 was the brute force approach. Just use a bigger, stronger servo. It would make the arm bulkier, but the design would be simpler to build and troubleshoot.
I always want the perfect solution that is cheap, compact, and looks amazing. But engineering doesn't work like that.
Eventually, I had to stop chasing the perfect design and focus on a robot that actually works. So I went for upgrading the shoulder for MG996R servo while keeping the other joints the same servo choices as PicoPal V1. Once I chose the new servo, I went back to on-shape, redesigning the shoulder joint. I chose to prototype only the revolute joint to start. Then I will build the rest of the shoulder arm link. One thing I really didn't like about PicoPal V1 was the assembly. Some screws were hard to reach. Some walls were too thin, and putting the shoulder together felt like solving a small puzzle. For PicoPal V2, I wanted the robot to be easier to build. So instead of adding big access holes everywhere, I opened up the side of the bracket. That made it much easier to insert the servo and tighten the screws. I also added bushings to reduce friction and wear in the joints. Now we're ready. Let's launch the print. Assembling the first prototype print started quite well. The servo went in super easily. We may actually want to reduce slightly the clearance and remove the cable cut to make the structure more sturdy. And there are mainly 3 things that need to be changed. First, assembling the servo horn was not very easy. Maybe we can add a positioning cut. Second, For bushing, extra clearance for the hole is definitely needed. Last, the wire is small, but the connector is not. Even if I couldn't mount the bushing, I still wanted to test the entire servo joint. So I assembled it without bushing. It rotates quite nicely.
How nice.
This test made me wondering, do we need to keep the bushing? So let's get back to CAD. Now it should be quite easy. Just print and assemble. Done. Unfortunately, reality is full of surprise. My print has warped. I still try to assemble the shoulder joint V2. Apparently, I decreased too much the clearance. Now the servo doesn't fit in anymore. The positioning cut definitely made assembling of the servo horn to be much more easier. But the 3D printed part cracked. Maybe the wall thickness is too thin now. Lesson for me, solving one problem often creates another one. This needs more iteration. Wow, the friction is quite big. And the tests without bushing showed clearly bushing is required.
Sometimes prototyping is the quickest path to get out of hesitation.
Finally, I increased the cable hole height, but apparently the width is still too small.
Version 2 actually worked less well than version 1, which was surprising and a little bit disappointed. But we don't abandon. Let's try again. Version 3.
Just first put the... Yeah, okay, cool. The bushing went in super easily. The servo as well. Just when the CAD design started improving, a completely different problem caught me. My prints started warping. At first, I thought the design was wrong, so I changed the model. Then I thought maybe the temperature was too high, so I lowered it. Even worse. I was quite frustrated. I searched online, I tried to use AI assistant to help me. I cleaned the bed, reduced the speed, changed the printing orientation. Some things helped a little, but nothing fully fixed it. And then I realized I was changing too many things at once. I could not really know what actually fixed the problem. So I became more methodical. I started changing one variable at a time. And the real fix was actually quite simple. Manually level the print bed with a piece of paper solved my warping issue.
And honestly, I was so happy. Not only because I finally fixed the 3D printing warping issue, but more importantly, I finally understand why and how to troubleshoot.
After 7 shoulder iterations, I finally finished improving the shoulder joint. Now let's start assembling just the shoulder joint side here. Nice, drops in very easily. Put the nut in. I put the servo horn in. And just put from the side actually. This is so easy to put. Oh, this drawing looks very solid. Next, I focused on the elbow and the wrist joint. I added the same bushing as in shoulder joint to reduce friction. I made extra cut so that the wrist can move freely. I also tried to improve the cable management for the forearm link. It was finally time to assemble the full robot. When I manually moved each joint, it felt much better than PicoPal V1. Each joint rotates smoothly, the robot can move freely and reach the entire range of motion. After weeks of redesigning, here's the PicoPal V2 assembled. Now we can wear it and test it. Gripper, wrist, elbow, shoulder.
Seeing the shoulder arm lift for the first time was incredibly satisfying. But moving is only half the story. Can it grasp?
I vibe-coded a simple user interface using an AI assistant. With this, I could move joints with sliders instead of rewriting code every time. Let's start testing. I tried to grab different objects by controlling PicoPal joint angles with the sliders. Sorry, I'm too excited. Oops. At first, the objects kept slipping because of the plastic fingertips, so I added a tiny strip of rubber tape to increase friction. And it completely changed the performance. PicoPal picked up the tape roll and the rubber perfectly. But engineering always has a last surprise. Okay, the elbow joint is not racking anymore. When holding a heavier object, the elbow servo simply froze. The moment the gripper let go, the elbow snapped back to life. My torque calculations were right. That smaller elbow servo is at its absolute limit.
At least now I know what's the next thing I'm upgrading.
I also manually recorded some waypoints so PicoPal can start arranging things in the pencil holder for me.
Before jumping into PicoPal V3, this project taught me a few lessons that could save you a lot of time.
First, do the math first. A 5-minute torque calculation can save days of redesign. Choosing the right motor from the start makes a huge difference. Second, don't fear prototypes. Every failed print answers a question that CAD never could. Debug one thing at a time. Whether you are debugging code or tuning a 3D printer, changing multiple variables at once makes it almost impossible to find the real problem. Last but not least, prioritize and build in stages. Don't try to make the perfect robot on day one. Get it working first, then improve it one step at a time. We will get to our goal eventually. This project took a lot longer than I expected. I thought PicoPal V2 would take about 2 weeks. It ended up taking more than 1 month. There were plenty of frustrating moments, especially tracing down 3D printing issues.
But every setback taught me something made the robot better.
Compared to the first version, PicoPal is much easier to assemble, the shoulder is finally reliable, and it can actually pick up objects consistently.
In the next video, I want to make PicoPal smarter.
Instead of controlling each joint with a slider, we'll dive into inverse kinematics, so we can just tell the robot where its hand needs to go in 3D space.
If you made this far, thank you so much for watching. If you are making your own robot at home, let me know in the comments what you are working on or what's giving you trouble. I'd love to hear about it. And if you'd like follow PicoPal as it gets smarter with inverse kinematics, computer vision, please consider subscribing. Take care. I'll see you in the next one.